Hello, my name is Ria. I'm a physics student here at the University of Portsmouth, and I've been working with the ICG for the last 4 weeks to develop the first ever prototype CanSat.
My name's Terry. I'm a student studying physics with astrophysics and cosmology at the University of Portsmouth, and this is a CanSat.
So a CanSat is something like this. It is roughly the size of a 330ml can, and inside of it holds all the subsystems you would expect on a normal satellite, so the ones that fly in space. The ICG's aim, along with Mission Space, is to create a UOP CanSat competition. So this will be open to university students within physics and other engineering degrees, and they will compete to make their own CanSat, and hopefully, if they're successful, launch their own CanSat. The competition is going to be running hopefully this year coming, and it's going to be really exciting to see what our students can make.
So CanSat is designed to basically test many of the things that satellites already do. So for example, one thing that your CanSat must do is it must be able to make a controlled landing from a height to the ground without braking. The other things you want to be able to do is you want your CanSat to be able to transmit data over radio in real time, and you also want to be able to make sensor readings. And there's a variety of things that you can record. So we have pressure sensors, humidity sensors, and also gyroscopic and accelerometer type sensors. And these are really good for figuring out the orientation of your CanSat, the height of which it is at any given time, and any of the external conditions that you're able to measure.
We've spent the last 4 weeks designing, modelling and creating the first UOP CanSat, and we started off by working our way through our sensor subsystem. So our sensors, they measure temperature, humidity, pressure, acceleration, and there's a gyroscope as well. So we created a little prototype first on a breadboard.
So a breadboard is essentially a way of prototyping electronics without having to make your final decision on where you want things to be. Here we have our breadboard prototype for our receiver station. So this is designed to basically take all the data downlinked from our CanSat and process it and store it. You can see we have a LED for telling us the signal strength. We have an SD card reader for storing our data. You can see here we have these holes where you can place pins. These right here. These here are jumper cables, and these will go into these holes on the breadboard. Now, if you plug something in here, this whole line is now connected to this cable. So anything else you connect on here will also be connected to this. The great thing about a breadboard is that if you simply don't like a component, you can just disconnect it. It's very, very easy to do debugging and all sorts of other things with your sensors just because of its ease for development.
We're controlling all our sensors with an Arduino. We're using the Arduino June, and we are programming this using C++. It's quite a simple program in the sense of we only have 2 sensors, as this is the first prototype. We hope one day in the future, when this becomes a competition, that these CanSats become a lot more extravagant, and they are really pushing the boundaries, and we can't wait to see what the students do with them. The way we prototyped ours was we attached our sensors onto strip board, as you can see, and then we wire wrapped and made our own homemade Arduino shield. This is a really good way of prototyping, as you can kind of test as you go along. It's a slow and steady process, but you get really good results from it, and it's a really sturdy bit of kit that you can put in your can.
This is the Arduino June. It's a microcontroller, so its main purpose is just to control electronics. It interfaces using C++ and the Arduino IDE. You can see here, this is the reset button. So when you press this button, it will reinitialize the program that is running on this central processing unit chip here. This chip also has storage to store your program, and there's also this port here, which will take any power from, say, a 9-volt battery and will convert it into a current that it can use.
This is our sensor subsystem. we have our accelerometer gyroscope on the left. Moving towards the right, we have our temperature, humidity and pressure sensor. To the left again, we have our LoRa radio transmitter. Next door to that is our SD card module. This prototype was made using our Arduino board and strip board. And if we open it up, we can see the insides of how we made our Arduino shield using header pins, wire wrapping and a fair bit of solder. This is sturdy enough to sit inside our CanSat and record all the data we require, and without getting damaged in flight.
So for communication, our CanSat uses LoRa radio, which stands for long range radio. It uses a range of frequencies that are available for public use without a radio license, so around 430 megahertz. And this allows you to basically transmit data at up to 2 kilometers of range at a fairly low rate, but this is not a problem for your sensors. After prototyping, your CanSat is going to be soldered into its final configuration. So here you have our final soldered CanSat, and this will fit right inside our own little CanSat here. So you can see this is our 3D printed capsule, which says UOP CanSat on the front. And this capsule is what holds all the electronics. So in here, our Arduino and sensor board will go. And we also have a battery, if needed, to power the CanSat too, which will also go into the CanSat. And on the other hand, we also have a parachute. This is about a 50 centimeter parachute. You must do calculations on how big your parachute needs to be depending on the weight of your CanSat, obviously. You can see it's connected with some nylon straps right to the lid so that you can quite simply just screw the lid on and your CanSat is ready to go. It's a very, very good project for students and people at all stages. It involves skills from physics, like looking into dynamics and mechanics, to electronics and mechanical engineering, and even CAD design. So it's a really good project that can go across many different disciplines, and it really can help you learn many new skills that you might not necessarily learn in your course alone.
To make it more complicated, you could do your own PCB boards. The possibilities are endless with this. We modelled our own CAN in 3D software, and it's all 3D printed in PLA, so it's so replicable, recreatable. And if one breaks, it's really easy because we can just print more. The total weight of our CanSat is 220 grams. Obviously, it's quite simple, so it's not going to weigh a lot because we don't have a lot shoved in there at the minute. But when they become more complicated, they'll become heavier. So then that's where that challenge lies. Unfortunately, CanSats cannot go into orbit like regular satellites. I really wish they could. Ours will be launched off drones from, I think we're hoping for as high as the drones can possibly go. So it will be a challenge for students to get their parachute deployed, to get it to land in the right place. There's many, many other factors trying to get it to land from a drone rather than up in space. So the maximum height a drone can fly in the UK is 112 metres, I believe. And our CanSat at the minute falls at 4 metres per second, only because we were launching it from a lot lower. When the competition starts running, they'll be moving a little bit faster, just because they're falling from a much higher height than we launched ours from.
Our CanSat was subject to a lot of problems. It's very normal to have your electronics not work correctly on the first time, or to go through many, many days of debugging. And it is part of the fun, in fact. It teaches you a lot about how these sorts of things work in real life. Most of these projects that are done in the space industry never work first time. So it's always very humbling to be able to realize that after all this work, your CanSat finally is functioning, and it really gives you a boost of confidence that you can actually do something like this. When we start encouraging more students to launch CanSats, we are hoping to have them be launched from anywhere from 50 meters and above. And that'll give it ample time to descend with the parachute and make all the adequate sensor readings. This CanSat itself was dropped off the ICG, and it was very, very successful.